Okay, question number 2 from the AP Chem quiz number 3. We're continuing with hydrocyanic acid right here. Okay, I seem to have lost my color bar. I've got it up here. Let's see what's a good color. Let's use blue. Okay, so now we're starting from the other perspective. We're starting with the conjugate base. Determine the pH of a 0.200 molar solution of your selected base. Okay, our base is sodium cyanide. Sodium cyanide dissociates into sodium ions plus cyanide ions. Okay, we don't worry about the sodium. We know the sodium is going to be a spectator. The cyanide, however, because it is the conjugate base of a weak acid, will undergo some hydrolysis to form some HCN, the conjugate acid, and hydroxide. The solution is going to be acidic. The solution is going to be basic. We've got a weak base. We know that the Kb for this reaction is equal to the HCN concentration divided by times the hydroxide ion concentration divided by the cyanide ion concentration. Don't you dare try to put water into that equilibrium expression. And from the information we're given, we know that the Kb is 10 to the minus 4.79. Okay, so as opposed to our acid, which was a very, very weak acid, we've got a relatively strong weak base. Okay? Again, remember this idea that the weaker the conjugate acid, the stronger the conjugate base, and vice versa. In any event, we want to figure out what the pH is here. As we've done so many times, we'll go to ice. My initial concentration of cyanide is 0.200 molar. I've got 0 of HCN and 0 OH minus. The change is going to be minus X plus X plus X. At equilibrium, 0.200 minus X, X, and X. Plug those into my equilibrium expression. X times X, 0.200 minus X equals 10 raised to the minus 4.79. You know the drill. X is going to be small. We're going to ignore the X in the denominator. Therefore, this simplifies to X squared over 0.200 equals 10 to the minus 4.79. You can all solve for X. When you solve for X, you find out that X, which is equal to the hydroxide ion concentration, is 1.8 times 10 to the minus 3 molar. The pOH of the solution, therefore, the pOH is going to be the negative log of the hydroxide ion concentration. The pOH is going to be 2.75. The pH of the solution, therefore, is going to be 14 minus 2.75, or a fairly basic 11.25 is the pH. That makes sense. The pH is greater than 7, and relatively high pH. This is a relatively basic solution because our conjugate base, the cyanide ion, is a significant weak base. Okay, I hope the idea of significant and weak put together makes sense based upon the Kb. So there we go. That's our solution of 0.2 molar of the base. Again, if you did the previous problem, compare the result here. We've got a basic solution. We started with nothing but the conjugate base. Now, we're adding HCl. What happens? Well, I've got base in my solution, Cn minus. I now add strong acid. I'm just going to represent that as H plus because we recognize HCl as a strong acid. It is completely ionized. So that 10th molar HCl is really 10th molar H plus. Reacts to form conjugate acid, and that's it. Okay? Good. So, what's going on here? Well, Again, set up our initial conditions, our change, and our equilibrium. Initially, I've got 0.200 moles of Cn minus. Again, a 0.2 molar solution in a volume of 1 liter. I've got 0.200 moles. I'm adding to that a tenth of a mole of H plus. And I initially have no HCN. What happens? The H plus reacts with the Cn minus. The Cn minus is going to decrease by 0.1. The H plus is going to decrease by 0.1. And the HCN is going to increase by 0.100. When the reaction is finished, therefore, my concentration of the Cn minus cyanide is going to be 0.100 molar. My hydrogen ion concentration is going to be essentially 0. And my HCN concentration is going to be a 0.100 mole. Notice what's happened here. I've got a situation where the concentration of the acid now is going to be the same as the concentration of the base. They both are going to be equal to 10th molar. By adding the acid, I've converted half of my original acid into its conjugate base. pH equals pKa plus the log of the base divided by the conjugate acid. And therefore, when I do that calculation, pH, the pKa for the HCN, again, pKa, we're looking at the pKa here, 9.21 plus the log of the cyanide ion concentration, which is 10th molar, divided by the HCN concentration with this 10th molar. That ratio is equal to 1. The log of 1 is 0. My pH is equal to pKa. I've created the best possible buffer. My pH of this solution is 9.21. If you did the previous problem, note that the answer here is the same as the answer we got in Part C. In Part C, we created a buffer, but we created the buffer in just the opposite way. In Part C, we started with the acid, added hydroxide to convert half of the acid to the base. Here, we started with the base, added the strong acid, converted half of the original base into its conjugate acid. Either way, we ended up with a situation where the concentrations of the acid and conjugate base were the same. pH equals to pKa, 9.21. The delta pH here is equal to the pH of B minus the pH of A. That's going to equal 9.21 minus 11.25. My delta pH is, didn't calculate that. I'm going to do that in my head. Watch out. I think that's a minus 2.04. Don't quote me on that. Okay? All right. Go to Part C. Guess what happens in Part C? In Part C, we're going back to the original solution in Part A, where we only have the base. We're adding hydroxide. Sodium hydroxide, strong base, completely dissociated. Sodium ions, hydroxide ions. The sodium ions are invisible to us. They are spectator ions. What happens? Cyanide is added to H+. We have two bases. We have cyanide. We have hydroxide. Weak base. Strong base. The strong base wins. The concentration of hydroxide in this solution is totally determined by the sodium hydroxide. So the hydroxide concentration is 10th molar. The pOH, therefore, is equal to 1. And the pH is equal to 13. Again, my change in pH this time, my final solution, 13 minus 9.21. Okay, that's going to be 3.89 is the pH change. Again, significant pH changes in both situations. Solution A is not a buffer. In this case, solution A only contains the base, cyanide. In question number 1, which I hope you looked at before looking at this one, the solution that we started with was the solution of only the acid, hydrocyanic acid. In order to have a buffer, you've got to have both the acid and the conjugate base. So parts B and C of both of these problems demonstrate what happens when you do not have a buffer present. Okay? The next problem we work is going to demonstrate what happens when you do have a buffer present. All right, I hope this makes some sense. If not, you know who to call.